distance and metric. Other one is a Rudin book, Function Theory in Walter Rudin. Function Theory. Unit ball. Euclidean ball. These two books are the reference for today's talk. Okay. First of all, let us start. The main class of interest of domains in several complex variables is pseudoconvex. I think that my voice is here for everyone.
Yes.
Please let me know. Okay. Pseudoconvex. I am not giving the definition of pseudoconvex. Our end of the talk is balanced. So, what are the simplest example of pseudoconvex domain? I think that most of the students in SCV, so they heard about at least pseudoconvex domain. Simplest examples. Every FCV book, you can see that the first example is Euclidean ball itself. Ball in CN with respect to L2 norms. Ball with respect to L2 norm. Another example you can see polydisc, or another way, ball. This ball we denote as delta n. Is a ball with respect to norm infinity. These are the simple examples. How can you generate? Can we generate more examples? More examples. You can take any with respect to any norm. Let B be a ball with respect to some norm on CN. Then B is also pseudoconvex. Okay. So some students not familiar with the pseudoconvex. Also, we can notate that these are the simplest example. Ball with respect to norms. That are the simplest examples. So, any ball with respect to norm, we get a pseudoconvex domain. The reason is that norm function is plurisubharmonic. Okay. Now we can ask the convex question. Question is how to characterize balls in CN. That means given a ball, given a domain D in CN. 1 minute. How to characterize balls in CN. What is that meaning? Given a domain D in CN. given a domain D in Cn, under what conditions? D is a ball with respect to some norm in Cn. How to characterize? First of all, we looked at what are the properties. If D is a ball, then what are the properties? We have suppose D is a ball. Respect to some norm in Cn. First, we look at what are the properties in this ball. Then we characterize that property. Is that property a sufficient condition for D makes a ball in Cn with respect to some? Suppose D is a ball. What are the properties? Basic properties. What are the basic properties? First one, D is convex. D must be a convex. Second one, simply D contains origin also. Convex domain containing origin. Containing origin. What are the other properties? D is necessarily a bounded also. D is convex bounded. My question is, these two properties characterize the ball. You can respond. Even we are not a typical class, we can interact. If you have a question, you can ask. I can also ask questions, so we can interact. My question is these two properties characterize the ball in Cn with respect to some norm. If domain D satisfies these two conditions,
maybe
question is
something like that. I don't know. Means there is a convex domain.
Handbrake theorem says that given a convex domain, we can separate some hyperplane.
Yeah, right.
Then you tell. I asked.
Okay, there is one more property that it should be Reinhardt domain. So is it covered in convex domain?
I guess balancedness,
if
like
I-
some sort of symmetry.
Yes. Because these two properties actually does not characterize ball edge. These two properties does not characterize that D is a ball. Because we have many examples. If a bound D is just a bounded convex domain, that need not be a ball edge. Then the main property is that is balancedness. That is our today's class. D is balanced. I will give the definition within a few minutes. D is a balanced domain. There's some type of symmetry for a domain actually. I will prove later actually. If D satisfies these three properties, then D is a ball with respect to some norm.
So balanced domain is means the third property is some kind of Reinhardt condition, right?
Yes. I will tell you. Result is if D is a bounded balanced convex domain in Cn, then D is ball. D is a ball with respect to some norm. We are going to explicitly find a norm actually, and then prove that D is a ball with respect to some. This is an interesting result actually. Proof is very simple actually, but this is an interesting result. We will see later the proof actually some result. we use this factor. I think everyone understood that. Any doubt, you can interfere that. Okay, let us start. The definition of balanced domain. A
Hi.
domain. Okay. Hi.
Wait, I have one doubt. On finite dimensional spaces, every norm are equivalent. So if D is a ball with respect to one norm, then D should be a ball with respect to another norm with different radius? This is like my
Actually,
question.
equivalent means the topology are same actually.
Norms are comparable. I mean, if two
And I'm
norms
sorry,
are...
norm 1 less than or equal to some C into some norm 2 actually. You say that.
Yeah, yeah.
Okay, comparable. But here we look more about if two different norms, there is some condition. That condition not about equality, it's about inequality. Norm less than or
Yes,
equal to some C in a norm.
the radius will
But
be changes.
Radius will be changed. Not only radius actually, this relation will satisfy. One norm less than or equal to C into some another norm.
Okay.
Okay, I am mainly focused on not only norm actually. I am mainly focused on balanced domain. Main question is, given a domain, suppose we have a domain D. Is D is a ball with respect to some norm? How to check that? Given a domain D, how to check that D is a ball with respect to some norm? That the main crucial thing I want to explore actually. Maybe some relations are there that I am not concentrated on that relations actually. I am relation this question actually. I written the result actually. If D is a balanced domain, then how to check that D is a ball? How do you know that D is a ball with respect to some norm? That norm is called, maybe you heard about the Minkowski functional actually. Okay. I focus on some type of, for motivating balanced domain. I initially started with the balanced domain, but my main focus not only on balanced domain, balanced some pseudoconvex domains. So I'm not interested fully on norm, how it is related to the different norms. I'm not fully interested. I am interested in this question, the result, first result. Is it okay?
Okay, you can carry on.
Okay. Yes, you said it's very correct actually. Finite dimensional norms are equivalent actually. That's fact actually. I'm not going that direction actually. Because that direction, we already have a result. Finite dimensional, most of them are equivalent actually. Here, this question I am focused. Because the main motivation coming from a convex domain, bounded balanced convex domain is a ball with respect to some norm. That is one of the motivation of balanced domain. Okay. The domain D is said to be balanced if the complex number lambda belongs to C with the lambda minus 1. Lambda is said it belongs to. For every set in D domain, lambda complex number lambda coming from the closed unit disk, and multiplying complex number lambda into Z belongs to D. That's a balanced domain. I will draw a figure what this geometrically means. So this is a domain. Okay. I take Z as here as this is Z. That what is the lambda dot Z condition is a lambda into Z. for every lambda with modulus lambda less than or equal to 1, lambda is in DH. That means geometrically for every Z in D, the disk connecting Z to origin is contained. Disk means complex disk. And disk is the total. This is a disk. You can assume that it's a disk. Disk. For every Z in D, the disk connecting Z and origin is fully contained in D. Is a subset of. That means for every line complex line intersecting with the D is a disk. That's geometrically means what is a balance domain. It is an analog of a star-shaped complex analog of star-shaped domains. You know that about the star domains. We already studied in RN actually. Okay, this is the
Hello, Jiju, bro.
okay.
This is star-shaped domain with respect to origin, right?
With respect to origin. Thank you, Berdi. With respect to origin, star-shaped generally with respect to needed to origin. With respect to some base point actually. Okay, this is a star-shaped domain with respect to origin. Thank you. I think balance. What means balance domain? You understood. Okay. Now we go to we talk about result actually. This is a balance. This is a bounded balanced convex domain. Then this is a ball with respect to some norm. What is the norm? That norm is exactly Minkowski is called a Minkowski function. So next we define the definition of Minkowski function. Definition. If D is a balanced domain, we can associate a function called a Minkowski function. This function is defined for Cn to R plus. R plus means real and positive real numbers including 0. We can define D of Z equal to infim of t greater than 0. Z by t belongs to t. This is the definition. T is a positive real number. We dilate Z by 1 by t. We check that belongs to D. We take infim of all such t. We can check what is this what means Minkowski function more precisely. We can return that it is written by 1 by supremum of alpha greater than 0, alpha Z belongs to. We can return that. This is more clear, right? What means Minkowski function? Minkowski function means we take a balanced domain. This domain, I take a point Z. I take a point Z. Instead, we can need to take in D itself, any point in the Cn, we can take it. I take Z. And this is the Minkowski functional HD means it measures the reciprocal of maximum dilation. Suppose I take Z here outside. I take it. Maximum dilation set such that some T naught Z belongs to. It measures the reciprocal of the maximum dilation of the vector Z such that the dilated vector T naught Z belongs to T. Or other words, we can say that here we take an Z HD. I take the line, complex line I take the, if L is a complex line, passing through origin, balanced dance means L intersection D is a disk edge with the radius some arrows. Or passing through origin and Z. Otherwise, Z has no road. Then R and HD of Z equal to 1 by R. This thing we obtain using the observation that HD of Z equal to 1 by supreme over alpha Z, alpha into Z belongs to D. Take any Z in D, place Z in C, take the dialects such that when it will intersect the maximum dilate such that it will intersect the domain. And take the reciprocal 1 by supreme
Hello.
over. Okay.
What is that? If L is a complex line through the origin and Z, then what is that logarithmic of D or?
Which, sorry, not log the L intersection is. Okay, L
Oh, L
intersection.
intersection. Sorry. Okay.
Yeah.
Thanks.
Okay. This definition is clear actually, rather than the first initial definition. 1 by supreme of alpha Z in D. You take this is the set. Again, just mention that, but this definition is very important actually. Z in D, take alpha Z. This is a alpha supreme alpha Z. Alpha Z is that alpha Z belongs to D actually. Such that alpha is a supreme. So then taking the reciprocal, that is the Minkowski function. I think as we go to the properties of balance.
Will this supremum be attained?
Okay. Supremum. Hello.
Will there exist some alpha that this will happen, or
Can you repeat the question? I cannot hear.
like I'm asking whether this supremum, will there exist some alpha
Exists.
in? Yeah, means it's a supremum thing, right? So whether that supremum will attained inside the disk only, or we need more condition on this.
Okay. Actually, supremum D is bounded and supremum surely exists. D is bounded and supremum surely exists. That means it's a finite number. If D is unbounded, your question is right actually. If D is unbounded, supremum, it may happen that supremum is infinite. Actually, we say that it does not exist, but supremum is equal to infinity. Actually. These two possibilities, either finite or infinite. D is bounded, surely finite, because every alpha Z, what is alpha Z means? The ray passing through origin. If D is bounded, the ray passing through origin is surely intersected boundary. This point. 1 minute. Maybe we can note that. The question is right. If D is bounded, then the ray, any Z, then for any Z, and for any Z and Cn, the ray alpha is equal to alpha greater than C, intersective bound. This implies that HD is finite. If D is unbounded, then HD of Z. There are some is unknown. There exists is unknown such that because that is not the ray does not intersect the boundary. alpha greater than 0. Alpha is not alpha greater than 0. Does not intersect the boundary. In such a case, actually, it is surely infinity. Because t is increasing, actually. This goes to infinity. The alpha is goes to infinity. But alpha is not, does not belongs to.
Oh,
I
but
think I
if
answered
we
you.
take D some upper half plane in R2, do we get
Because
some?
we are focusing on balanced domain.
Yeah. Okay. No. Here in the second condition, you said D is unbounded.
Hmm.
So if you take D is a upper half plane in R2, do you get some Z naught such that HD of Z naught is infinite? I think you may need two-dimensional unbounded domain, something like that. Means you need, I think, the domain which is the complex line, like.
Actually,
Mhm.
one thing actually, I hear balancedness is crucial actually. These an upper half plane, something like that. This is
Yeah.
origin actually.
Mhm.
Then it is not maybe it will go this side actually. The line, complex line. Okay.
Okay. So
This line
in your okay, so
then
you are
does not.
saying if D is unbounded and balanced, then there exists Z naught.
Yes. Yeah, I'm talking about entirely about balancedness actually. So
Okay.
initially I started with the balancedness. In the entire talk, I am assumed that it is balanced.
I see.
Because if it is not balanced, I cannot define Minkowski function. Why?
Mhm.
Because z by t. So we can some z by t belongs to d. The basic properties we looking for, we prove that later. But if d is not balanced, we cannot. We can define actually, but some properties will be lost.
Okay, so we are assuming D is balanced. Okay.
D is balanced. This thing will come to later also after defining properties. I will. Thanks for the good question. Next properties. First properties. Property. First property is HD of lambda is equal to modulus lambda into HD of z. Proof is very simple actually. Because I'm not planning to boring you. I will tell some key things actually. What is HD of lambda is a proof. Just quickly tell the what is the key. HD of lambda is means set of all t greater than 0. Lambda is set by t belongs to. We want to show that. If suppose we show that modulus lambda suppose we show that it is modulus lambda s greater than 0 such that is z by s belongs to d, then it is done. This set actually. This is infime actually. I'm not taking the HDF. Consider the set. This infime of this set. Consider this set. These two sets are equal. If these two sets are equal, it is done. How to these two sets are equal? We using the property of balancedness. Consider suppose there is a t such that lambda is at b, t belongs to. Since d is balanced, then we can write actually modulus lambda by what, right? Modulus, we multiply lambda is by t by modulus lambda by lambda. Then also it belongs to d because d is balanced. That means modulus lambda z by t belongs to D. This we can write as z by s belongs to D, where s equal to t by modulus lambda. S is equal to t by modulus. That means these two sets are equal. So that and then taking infimum, then we get that HD of lambda is equal to modulus lambda. One thing to observe is that actually for this definition, okay, no problem. This is one property. Next we go to second property. Second properties will determine the balancedness and the Minkowski function. What is the relationship? If D is a balanced, then D equal to D is exactly equal to set of all Z belongs to Cn HD of Z. This is very simple. I'm actually not proving it. Telling because if he said in D, if Z belongs to D by the definition of HD of Z. What is the definition of HD of Z? Mr. Go to the definition. So if Z belongs to D, if T equal to 1, the 1 belongs to this set. This set 1 belongs to this set. So HD of Z surely less than 1. Z in D, HD of Z surely is. If HD of Z is less than 1, that what is that meaning? There is a T naught less than 1. I will write HD. By definition. HD of Z less than 1. Then there is by definition there is a T naught such that less than 1 Z B by T naught belongs to D. We multiply T naught. Since D is balanced, multiply by T naught, we get Z belongs to D. Okay. So this is very simple actually. This is determined. D is determined by Minkowski function. This is that means D is D equal to H less than. So naturally another question will come. Question is boundary of D. If D and the domain D is Minkowski function, sublevel set of Minkowski function, then what can you say about boundary of D? Is boundary of D is exactly same as H of Z equal to 1. What is your answer? Is it true or not?
It should be true, I guess. If D is balanced.
D is always balanced, but answer is not true actually.
Oh, I see.
I will actually I didn't write the explicit expression of the domain D. I will draw a figure actually. No. This is a domain. You can take consider some Euclidean ball also. You can take and take the slice. This part actually. This is a balanced domain. Picturely, we can see that because what is the meaning? Every line, we take it any complex line, it will take any complex disk Z for any Z in D, taking the disk spanned by connecting Z and origin is fully contained in D. Take any Z. Why it is not true? Boundary D is exactly H equal to 1. Can you tell why? I think it's clear that it's a balanced domain. If you take any complex line, intersection is a disk. Here also, if you take any complex disk, it intersects D is a disk actually. Why it is not true? Boundary D is exactly equal to H equal to 1.
Because if you take Z in this somewhere in this vertical line, then
Okay.
Z may not be 1.
Yes. Here is this point is a node. If I take equal is a node, here H of is not equal to 1 because it intersects with the boundary actually. The definition of Minkowski function is when it will intersect the boundary, that maximum point actually. That point is got some t. This is a node actually. This is a node. H of is not equal to 1. But I take this one actually. This point dilate t into is a node. T is a greater than 1 actually. Some t greater than 1. Here t is a node. H of t is a node is greater than 1, not equal to 1. So, the boundary D is not exactly equal to H equal to 1.
So here is one question. So here domain is not in, at least it should be in C2, right? It should not be in C, at least from this example.
Okay, C
this
intersecting
domain is a subset of Cn where n is greater than or equal to 2, right?
Oh, yes.
Yeah.
Yes.
So
one thing
so
is
is there an example in the complex plane or is in the complex plane this question is true? Means the boundary is exactly H is equal to 1.
Oh, okay. That's a good question actually. I also missed that. If dimension n equal to 1 actually, it doesn't happen. Why? In dimension n equal to 1, what are the balanced domain? Maybe you know that. In n equal to 1, dimension 1 complex variable, what are the balanced domains?
Disk.
Disk, yeah, ball. Yeah,
Yes, disk and any disk of arbitrary any radius actually.
Yeah, disk
not
with
unit
any.
disk. Okay. Disk. So in dimension 1 actually there is no point for studying for balanced domain. Only discuss the disk we know that. But in several variable, if you any greater than 1, there are many domains, different type of them. One example is this one, this domain.
So interesting case is higher dimension.
The higher dimension. Interesting case is higher dimension. Yes. Correct. One more thing to tell that. I told that I will draw a figure actually for convince you. But the explicit expression takes more time and takes complicated. If you want to look for explicit expression such that this does not happen, refer Jarnik book. Okay. So it's a little complicated. Minkowski function a little complicated. Okay. So that's why I'm not going to that. He said that this equality doesn't hold, but one inclusion is one way inclusion is always hold. That we cannot. Property 3, not a property 3. Property 3. This is always true. H of is equal to 1 is contained in boundary of T. It is easy to prove. If H of is equal to 1, is always contained in boundary. Using the definition of boundary of D. Boundary D means if that in boundary D, every neighborhood intersect D and D outside of D. I think it is clear. I'm not proving that. If anyone wants, I will tell you. And also use the fact that D is if D is a domain, it is less than 1. If h of z is a Minkowski function is 1, then it must be contained in boundary of D. Okay, but we saw that the converge is not true actually. But when the converge is true, that is the next question. Property 4. If Minkowski function is continuous, then boundary D equal to exactly equal to one inclusion is to how to prove that reverse inclusion is easy actually. Anyone can tell that anyone get the answer, please let me know. How to show that? Here actually it is not true. Why it is not true? Here it is not continuous. This example, domain D, it is not continuous. Anyone tell the proof of the 4?
So like take Zn which is in D so that it will go to Z0 on the boundary D, then we know Hzn is less than 1 and Zn goes to Z0, then Hz0 should be less than or equal to 1. If it is strictly less than 1, then it is in domain otherwise.
Okay, suddenly then we can choose a sequence actually. Choose a sequence. I will write the proof. Zn in D such that Zn converges to Z. But we know that by property 2, h of Zn is less than 1. H of Z and h by continuity of h. Here we are using continuity of h. Z is in boundary, not in D. So we can get that by continuity of h, we get that h of Z equal to 1. Actually, by continuity, we can say that h of Z greater than or equal to 1. But Z in boundary of D, h of Z must be equal to 1. Okay. Let us go to next property. One more thing actually. One minute. Okay. Let's we go to not property, some type of result actually. Some observation. I will call observation. Here is the problem in this domain actually. This domain. The problem is this ray. We take a ray. Consider the ray spanned by Z0. T Z0. This ray intersect a boundary more than 1 point. This ray intersect a boundary more than 1 point. That's why it is not equal to the boundary. Boundary D is not exactly equal to h of Z equal to 1. So we can get another characterization such that boundary D is exactly equal to if and only if for every Z in Cn is not equal to ray. Is not the ray intersects boundary at most 1 point. and in boundary. Then these are equivalent actually. This is also easy to prove. It's some elementary check actually only. So I'm not proving that. This is geometrically it is very interesting actually. Boundary is exactly equal to 1. That means every ray intersecting the boundary at most 1 point. If D is unbounded, it need not be intersect the boundary. If D is bounded, it must intersect the boundary. Intersect only 1 point. This is the some geometrical characterization of this condition. Other property, this property.
So is it at most or exactly 1?
At most actually, because if D is unbounded, it does not intersect the boundary.
Right. Okay.
That is it may happen that.
Yeah.
And next question related to that one. Give an example of balanced domain. D such that and D and is not belongs to D such that HD of is not equal to 0. Z0 is non-zero. Z0 is a non-zero point such that HD of is not equal to 0. Can you give one example? Such a domain are always unbounded actually. Balanced domain.
Yeah, take Cn.
Cn is true. So the proper subset. Cn is always true actually. Proper subset.
Yeah, then take some tube type domain maybe.
Okay. Maybe I will take as maybe take a tubeless, not like to this domain you maybe see in a civic course. This domain is set for ZW in C2 such that what is ZW less than 1. Look this axis actually. This axis is contained in D, but does not intersect domain D. And not domain boundary of D. It does not intersect the axis Z equal to 0 and W equal to 0 does not intersect boundary. So HD of 0 W, 0 any W equal to 0. Or similarly HD of H of Z0 equal to 0. Because it does not intersect it. You can take any scaling actually. Any scaling of this point, it does not intersect the boundary. Okay. Next we go to the property 5. Property 5 says that related to this boundedness actually. If D is bounded, then Z inverse of 0 equal to 0. We already discussed that if any Z in Cn, if D is bounded, the ray passing through origin in the direction of Z must intersect the boundary. So we can we can attain a bound for infimum actually. So HD is not equal to 0 for any Z not equal to 0. So I'm not proving that. This is very basic thing. Last very important thing. We in the very start, the beginning of the class, I wrote a result actually that I am trying to prove it. One is D is convex, balanced convex domain. If and only if H is a semi-norm. The homogeneity property, we check that HD of lambda is equal to modulus lambda into H of Z. The only property we check that triangle inequality. We have to show that for all Z W belongs to C. Maybe may see the proof actually. Maybe I quickly tell the idea. Z and W in Cn by definition of Minkowski function. For each epsilon greater than 0, there is a t greater than 0 such that Z by T belongs to D and T less than H of Z plus less epsilon. Similarly, there is a S greater than 0 because H of by the definition of Minkowski function of W such that W by S belongs to D and S less than H of W plus epsilon. Hence, we compute H of Z plus W by S plus T. Just say we take Z plus W by S plus T. That way we can return that T by S plus T, Z by T plus S by S plus T, W by S. Okay. We can return this combination actually. This is the convex combination. We already know that Z by T belongs to D. This T, Z by T belongs to D. W by S belongs to D. So convex combination also belongs to D. That means by the property 2, H of Z plus W by S plus T less than 1. H of Z plus W less than S plus T. What is S plus T? S plus T is less than H of Z plus H of W plus 2 epsilon. Since epsilon is arbitrary, we get the inequality. This is the triangle inequality. If D is convex, H satisfies the triangle. Then we proved our earlier result. If D is a bounded, convex domain, then HD is a norm. Because if D is bounded, HD of Z equal to 0 means Z equal to 0. Norm on C. That means D is a ball. Therefore, D is a ball. The sum now, that actually not sum now, this is exactly Minkowski function. HD. This is the goal of today's talk actually. If you have any question, you can ask. So D is a bounded balanced convex domain. We can always say that D is ball with respect to sum now.
Like this all can be done for any topological vector space also, right?
Topological space we can extend actually. Convexity is required. Some maybe functionality you saw that balance if D is balanced, then we can extend to this property to topological space also. Yes. There actually have something called absorbing space, something like that. If you functionality is ruled in book, Actually, this is common. You can see this proof in functionality test book also. Balanced domains also always discussed in function analysis. Actually, today I want to take some more actually, but time is almost over. I want to go to actually plan for some properties, not properties, some result related to balanced domain. But maybe if I get a next class, I will discuss about interesting result about result regarding balanced domain. If anything, any question you can.
Question. So the last result you just wrote, right? You did not prove, I guess.
Which one? This actually, actually maybe proved because by the last property we get if D is convex, it is a semi-norm.
Okay.
Okay. Fifth
Yes.
property, D is bounded, HD is 0 equal to 0. If these two property 5 and 6 we get
okay, then we'll get the result. Okay.
HD. Okay.
I see.
Some,
But
okay.
but I think you have proved the one part, I guess, means the converse or no
Which one?
backward or the forward. The sixth part means you proved, I think, the forward part, right? Means if
Then
D
also
is
it is a semi-norm. Okay, that is also we can prove that. It is a semi-norm that D must be a convex because what is the definition of convexity? And then maybe we'll try actually. I will try.
Okay. No worries. I'm just confirming, miss.
Okay.
It will be easy. Yes.
Okay. Some things are easy. That's why I skip the proof actually because too elementary actually. It may be boring for you also. That's why.
Yeah.
Okay.
Yeah. Okay. So, is there any question? Okay. If not, then let's thank Jiju Mammen. Okay. Then we'll meet maybe next week.
Okay. I will do. Okay. Thank you.
Thank you. Yeah.